Hi everyone, in this video we will discuss on the digital to analog conversion in the microcontroller. So for the microcontroller, the digital to analog converter or DAC is used to convert the digital value from the microcontroller to the analog voltage at the microcontroller pin. So the conversion, the analog voltage can be obtained by using the same formula with the ADC, where the equation is rearranged like this, where V out is the analog voltage at the output equal to D digital input from the microcontroller divided by 2 power of n, where the n is the size of the DAC multiplied by the V reference VR. For example, if our DAC is 8-bit and digital input from the microcontroller is 30 in decimal, right? So our Vout is equal to 30 and DAC is 8-bit, means that the total number of digital value will be 256 and multiply by VR, which is 5. So this is equal to 0.6 volt. So the Vout will be 0.6 volt. Alright, so this is the staircase graph, just like the ADC, where we have the digital representation here, and this is analog voltage. So with digital value here, we can convert to the digital voltage by using the this equation, so we can get a analog value, just like the previous example. So let's go faster here. So this is the same theory. So this is the same information as the ADC, but we need to know that the LPC1768 has 10-bit DAC, means that the size of the DAC is 10-bit, means that you can have up to 1024 digital number that can be converted to the analog value. And the analog output for the microcontroller is at pin P18 here. So we have only one output, analog output. And this is the function to create the analog output, analog out. This is the embed function that we will use to create the analog output later on. Let's look at this example. So for the analog out function, the value that you can use for analog out is between 0 and 1, just like the analog in function, where if you want to create the analog value of 0.825 volt, what you need to do is to have 0.25 multiplied by 3.3 volt to get this value. All right, so in your program you need to assign A out, which is your analog out name, with 0.25, so the output will be 0.825 volt. And if you want to output 1.65 volt, so you need to assign A out with 0.5. This means 0.5 will be multiplied by 3.3 volt, and you will have this 1.65 volt. And for 2.475, you need to assign 0.75 to A out, such that you get the 2.475 volt. So this means this A out analog out function, the value is between 0 to 1, which is the normalized value. So 0 will represent 0 volt and 1 will represent 3.3 volt. So if you want to have half of this value, which is here, so you need to use A out equal to 0.5. Then you get the value in the middle, which is 1.6 volt. Now let's look at the next example where we have a for loop here, where A out is now assigned to a variable I, and I is start from 0, and while it is less than 1, and it is increased by 0.1, means that initially I will equal to 0 and then send to the A out. So A out will be 0 and wait for 0.001 second or 1 millisecond. Go back again, and now I is updated to 0.1 and output send to the output and update again until I is more than 1. So if I more than 1, so it will reset to 0 again. So this will create the sawtooth waveform. So the output will be something like this. When I equal to 0, the voltage at P18 will be 0. And after 1 millisecond, when I equal to 0.1, the output of the at the P18 will be 0.33, because this is due to this 0.1 multiplied by 3.3, so you have 0.33, and another 1 millisecond, so you will have 0.66, and so on until you have how many times? So 0.1, 0.1, 0.2, 0.3 until you have 0.9 multiplied by 3.3, and it will go down and start again. So this is the sawtooth waveform. Now let's run this and see the output on the oscilloscope. So now this is the program on the embed compiler. So let's decompile the program. And save in the embed. And let's have the oscilloscope here, the scope. Right, so this is the sawtooth that we create. So let's reduce noise so that we can see the output clearer. So we have this. Okay, so we have this is 0.33 volt, so we can measure actually from this to this, and exactly 329 millivolt or 0.3 volt. And we have how many? 1 2 3 4 5 6 7 8 9, and then go back to 0, and each width of this is should be 1 millisecond here. All right, so this is the sawtooth that we create, and let's go back to the compiler and have another example. Let's look at this example where we have here is the increment in the step, and this, instead of reset to 0, now we decrease by 0.1 until 0, and decrease and increase back and decrease again. So let's see the output. Right, so let's reset this, run. So we have the output here is yes, so we increase and we decrease, increase and decrease. So go back, so this is not increment, actually this is decrement in 0.1. All right, now this is the sine wave, where we create the sine wave from the analog out function. And let's look at the program where we have the sine wave program here, and this is the program to create the sine wave. A out is equal to 0.5 plus 0.5 multiplied by sine I pi, and this is to compute the full sine wave, and the resolution is 0.01 for I. So let's run the code and see what happened. So we reset microcontroller, and this is our sine wave. Yeah. All right. So for the conclusion, so we for the microcontroller, the LPC1768, we can read the analog value and convert to the digital value such that we can process in the microcontroller, and also we can create the analog output by converting the digital value in the microcontroller and send to the output pin in at P18 for the analog out. And this is the example of the analog voltage that we can create using the analog out function. All right, so that will be the discussion on the digital to analog conversion. So for the next video, we will learn how to produce the PWM signal. So for this video, thank you and goodbye.